Hello and welcome. In this video, we will do a crash course in single and multivariate chain rule. So in our first calculus course, we learned about this thing called the chain rule, which says that if you have a function that is comprised or composed of another function, which depends on another variable like x, then to find their derivatives, you take the derivative of f with respect to g, and then you take the derivative of g with respect to x and you multiply them together. So it's not unheard of that we might have seen something like where we need to take the derivative of, let's say, maybe something like 3x plus 2 quantity squared. And so the way we would do that is we would take the derivative of, we would kind of think about this as u squared, where u is equal to 3x plus 2. And so the derivative of u squared is 2u, and the derivative of u equals 3x plus 2 is just 3. So when we multiply these back together, and of course not using u, but using what u represents, then 2 times u would be 2 times 3x plus 2 to the first power. So we basically use the power rule there. And then the derivative of 3x plus 2 is 3. So we would have taken the derivative by basically taking the derivative of the outside multiplied by the derivative of the inside. Well, a much more intuitive way to think about this is by sort of this dimensional analysis, where what you're really doing is this is f prime g is the derivative of the function with respect to the substitution. So like the derivative of 3x plus 2 squared, the derivative of the outside was 2 times stuff to the first power, multiplied by the derivative of the inside with respect to x. So when you multiply those two things together, the reason this works out is that you can see the dg's cancel and you just end up with df over dx. So the way this would work with something like y equals 3x squared and x equals 2t plus 1 is we would, first of all, to find dy dt, we can set this up very easily when the variables change by saying, well, I can take the derivative of y, but I can only take that with respect to x, and I can take the derivative of x, but I can only take that with respect to t, and look at that, the units cancel out. So the derivative of 3x squared with respect to x is 6x, multiplied by the derivative of x with respect to t, the derivative of 2t plus 1 is 2, so we end up with an answer of 12x. But here's the thing, we wanted the derivative with respect to t, so the last thing we should probably do here is to get this equation in terms of t. Well, x is equal to 2t plus 1, and so to have this function as depending on t only gives us 24t plus 12. Now, to understand kind of the logic of why we do this, let's think about a way that we could basically construct a pretty cool diagram that shows us the chain of dependencies. So you can always build this, and that's the beautiful part. First of all, at the top, put your dependent variable, which in our context was y. All right, so here we have y. And what's y's most direct dependency? Well, y most nearly depends on x. So here is x. And then x depends on another variable, which is with respect to t. So this chain of dependencies shows us that if I want to relate y to the variable t, then what I can do is I can follow the chain down and observe that, first of all, y and x have a derivative, and that's going to be dy dx. And x and t have their derivative, which is dx dt. And then by building this chain, all I have to do now to find dy dt, which is what I want, I just have to multiply the chain of derivatives, which is dy dx times dx dt. And the beautiful part is this will always work, even in the situations where you have a multivariate problem. So for a multivariable chain rule, oh, and by the way, this could be something like the cost of gas. So let's just say that this is the cost of gas, cost to fill gas tank. Well, what does that depend on? Well, that depends on how many gallons you get, right? So you're going to get X gallons. Well, how many gallons you get is going to depend on something else, like maybe your car type, the size of your gas tank. So the size of your gas tank will determine how many gallons you get, and how many gallons you get determines how much cost you'll pay for. So you can see that there's oftentimes dependencies among multiple variables. Now, in multivariable calculus, Z depends on two inputs. It depends on both X and Y, and those are its direct dependencies. But here we see that X is a function of time. So here there's some other variable that X depends on. It's a function of time. And Y is a function of time as well, so to know Y, we would have to know the value of T. With this chain of events, as long as we list out all of the different derivatives, so Z and X will have one, dz dx. Now notice I'm using the partial derivative operator for dz dx and dz dy because Z depends on two inputs. Down here, X and Y each only depend on one input, so I'm going to use the old standard calculus notation, dx dt. There's not more than one input variable for X, so I don't need the partial notation. You will still see some people use the partial X, partial T, which is fine, but again, to stick with why we use the notation for partial derivatives, it's because we use it in events where there's more than one input variable. But X only depends on T, Y only depends on T. So we'll have dx dt and dy dt. Now there's two routes to get to T, right? There's one via X and there's one via Y. So the way we can think about this is how Z changes depends not only on how X changes, but also on how Y changes. So to construct dz dt, what I have to do is first of all look at how Z changes because of X. So dz dx multiplied by dx dt. And what you notice here is the changes in X cancel, and there's a dz dt right there, which matches up with the units. But this is what we can call the change in Z due to X. Change in Z due to change in X. Okay? And we can, or I would say change in X, because we're probably only going to change one variable. We're only changing the value of T. But because we change the value of T, that changes X and that changes Y. Plus, we're going to have the change in Z due to the change in Y. That's following this chain down, going the other direction. So that's going to be dz dy multiplied by dy dt. Again, we want the dy's to cancel. There's our dz dt. And this is the change in Z due to change in Y. Now this applies across multiple spectrums. You could have Z depend on three input variables. Let's say W, X, and Y. And these three could depend on their own things. For example, let's say W just depends on some variable that we're going to call S, and X and Y both depend on some variable that we're going to call T. Well, in this case, again, to get the total change in Z, I have three terms that this equation is going to have. There's going to be a dz dw, there's going to be a dw ds, there's going to be a dz dy, and there's going to be a dz dx, and then there will be dx dt and dy dt. So if I follow this chain all the way down, I see that the change in Z related to, let's say the change in time, well, I can see that W is not going to change when T changes, therefore this is only going to have two terms in it, unless, of course, W is also linked to T, and then we would have three terms that would be associated with the change in T. So let's write this out as such. Let's say this will be dz dx, because X depends on T, and there we get 1 dz dt, plus the change in Z due to Y, and the change in y due to t gives me, again, all the changes that are caused by t being adjusted. Now dz ds would only consist of one term because if s changes, it will only impact w. So this will be dz dw, following this chain to get to s, times dw ds. And again, you can see that's our contribution. One last situation which we often see and that we want to be able to handle and take care of is the situation where, well, it's kind of the same situation as up here. Let's say that z is a function of two inputs. It depends on y, but it also depends directly on t. And then the value of y actually depends on the value of t as well. So z will change via two things, right? It will change because of y, and y will change because of t. And then z has a direct correspondence to t as well. So maybe, oh, well, I won't give a applied example because I think it'll get a little convoluted. But we have dz dy, and we have dz dt. Now the reason I'm writing this partial operator here is because z depends on two inputs. But y only depends on one. So depending on how many links are coming, or how many edges are coming off that link, will determine whether it's a multivariable function or not. Okay, so to get dz dt, there are two ways to get there. There's via y, so that will be dz dy times dy dt. So look at the units there. And there will be that direct link, dz dt. And so we have this term right here, which corresponds to going this route. And then we have this term here, which is that link right there. So this is how the multivariate chain rule works. Again, you can keep drawing the diagram out. It can get very complicated, but as long as you're following all the different paths and writing one term per path, which in some instances it may be a product of two separate factors, or it may just be a standalone term. This is how it works.